All right, good afternoon. So here are the results of the second midterm. Mean was 137, it's the 55 percentile, and you can see this is perfect. No curve, it's all just sort of like a straight line across the spectrum, and that's exactly what you want, to spread out all of the scores, because the worst thing that can happen is that at the end of the day, 1 point separates an A from an A minus or something like that. So obviously, if you're up here, and there seems to be a bunch up here really quite good, I mean, you're doing very well. Remember, however, those of you who are further to the left, that this is only half the number of points so far. So the final will be a total of 500 points. It'll weigh as heavily as the two midterms before that. So nothing's really lost. And in many cases, what you do in the final will really determine what your final grade will be. So my advice for those guys up here, keep it up. Okay, it's going to get easier now. The last third of this course, starting with the chapter 22 today, it will be a lot of revision. No new functional groups. We'll discuss how all functional groups interact when there are several of them in the same molecule. So there are some new strategies that will open up, but a lot of the basics will stay the same. Okay, or there'll be an extension of something that you've already learned. So that will cause the stuff that we learned for this midterm to sink in and solidify. So typically the average for the final is way higher than the second midterm. Second midterm is in fact always low, relatively speaking. And if you remember the average for the first midterm, it lost about 20 points. Okay? And we'll recover that for the final. Those of you in here, so it depends very much on the individual, so I'm generalizing here. But those of you here, there may be a number of you who are perfectly happy with this, and I encourage this. You're just taking this course to fulfill a requirement, to pick up some basic organic chemistry, and you're doing well. I mean, that's exactly what the C plus or B minus grade will reflect, that you actually picked up a lot of stuff. Maybe you didn't go in with total rigor, but you're fine with that, and nobody's going to penalize you for that. In fact, I totally welcome that. Okay? So there are many of you who are in this regime, and for those people, I say just keep it up the way you've been doing it, and you seem to be doing fine. Over here, that is, again, a tricky issue. You should look at your exam, should look at what's going wrong, what you don't get, whether your strategy is right. You may focus on stuff that you're good at and make sure that you nail those questions in the final. Maybe you need to reorganize your schedule. I don't know. It's a highly individual scenario. But one thing that should be said at this stage is that if you're down here, you're not failing. Okay? The term fail is a total misnomer. Okay? It's a disaster, in fact, because it instills in you the feeling that you are nobody, okay? That you're, you should be wiped off the earth. And of course, that's complete rubbish. Okay? What university is for you to find out what you're good at. And the corollary of that, of course, is that you'll find out what you're not so good at. Okay? And chemistry could definitely be one of them. Chemistry is an acquired taste, and some people it just doesn't click. Okay? I've had subjects like that where I just was bored stiffless, 2 tears in class, and consequently I didn't do as well. Even though I worked extremely hard in attaining a reasonable grade, I just didn't do as well because it didn't interest me or just didn't click. Okay? It's just like sports. Okay? You can train for the 100-yard dash as much as you want, but you won't go beyond a certain number of seconds or minutes, as the case may be, to run the distance. And you can train over and over again, beat your head against the wall. You won't be able to do it. Okay? So then you have to say, okay, I'm just not good at this. And if this course somehow seems to be a cornerstone of your future life, sit down and look at it and say, well, I'm not good at it, I'm not having fun at it. You want to do stuff like that for the rest of your life. So that's what university is really there for in terms of finding your niche. Okay? So there's nothing wrong with saying, throwing the towel and say, this is not for me. I'm glad I found out now, rather than finding out at age 45 when your spouse and children and dog will leave you and you have to go to psychotherapy in midlife crisis. There was a question up there. Did I answer your question? Okay. So, so it's a good time for those of you who are just not doing well because it doesn't click, to rethink what you want to do. For those of you who are pre-meds, yes, the course is taken as a plus if you're doing well in this course for applications to med school, but not doing so well in this course is not a shutout. Okay? It's not, the door is not locked. And in my experience, I've got many students who got a C, C plus, B minus, whatever in this course, and they go into med school. Okay? Because a lot of it depends on letters of recommendation and other things that you're doing. Okay? So it may be a plus, but it's not a complete minus in your application. Yeah, so that was a question. Where would I say the cutoffs are? I have no idea, really, except that you can divide. I mean, I start grading by dividing all the grades in equal numbers. So every grade has 12% or something, right? So A plus doesn't count. That's up there. Then A, because you don't get grade points for it. A minus, B plus, B, down to the F. And everybody gets the same percentage. And then I start working with that. I look for breaks, and I typically move the grades up as I work my way down. I look at individual exams at the break points to have an absolute measure of, is this really still an A or is it an A minus? And then so things come from there. Okay? So it's hot. But that's if you divide them up into percentages, that's the worst case scenario. It's not going to happen. So better than that. And I'm shooting for a C plus average, perhaps even B minus. Okay, so much for that. So we've been talking about the means, and you've noticed already that this chapter has a lot of review. Very little new stuff, actually fundamentally new stuff, none really. Everything is either a revision of what we've done before or an extension of chemistry that and a new application. So, for example, the Gabriel synthesis, which allows you to introduce a single substituent onto a nitrogen. And so now we're going to look at reactions of amines, and I'm just focusing on the new reactions because some of the old reactions we've already covered, for example, SN2 chemistry of amines, alkylation, turning one amine into another amine, and the like. And there are only 3 of them, and at this stage, really only 2 of them are of vocabulary consequence. The third one will be a piece of vocabulary that will postpone in its application to the next chapter. So the first one is the so-called Hofmann elimination. This is the same Hofmann that we saw in the Hofmann rearrangement and in the Hofmann rule in chapter 11, for E2 type eliminations. So he was interested in seeing whether, extending the analogy of amines to alcohols. And in the case of alcohols, remember, one mode of reactivity of alcohols is that in the presence of acid, you can turn the OH, which is a lousy leaving group, into water, which is a good leaving group. And depending on R, typically for R secondary and tertiary, the leaving group leaves, and you get an SN1 type or E1 type process via the carbocation. And so, and if you turn, and for primary alcohols, if you turn this into a proper leaving group, say the tosylate or the mesylate or the bromide or chloride by the appropriate chemistry, then you can do E2 chemistry with a strong base, like tertiary butoxide or LDA that you've used extensively. Okay? And so he thought maybe this will also work for amines. Now, with amines, there is the problem that amines, of course, are much more, how shall I put this? They're much more basic. So protonation is much more readily done to an ammonium system, but they're much worse leaving groups, okay, than water. Okay? So ammonia is a much worse leaving group than water. It's the corollary of saying water is a lousy nucleophile, whereas amines are very good nucleophiles. Okay? And so this is not applicable. The SN1 type process, the exact analogy is not applicable. But Hofmann found that if you turn the amines into quaternary ammonium salts, that is all substituents of the nitrogen are alkyl groups, no protons, then in fact what you can do is E2 reactions, E2 eliminations. In other words, it does turn into a leaving group that functions as a leaving group in E2. So in other words, you have an ammonium system that on its own won't leave because the nitrogen is not a good enough leaving group because it likes to stay. Okay? It's more basic than water. But it can undergo an elimination by E2 if you treat a species like this with an appropriate base. Notice that this, of course, by definition, therefore, can only happen for cases where R is an alkyl group, because if you had a proton sitting here, it would be an ammonium ion. The pKa of ammonium is 10. You hit it with hydroxide, it will just deprotonate. Okay? So it has to, basically, the nitrogen is blocked from deprotonation. There's no proton left. And then, indeed, you can do an E2 elimination. And what it does is it cleaves the carbon-nitrogen bond, and you get an alkene, just like with other E2s. Okay? So it's basically an extension of E2 chemistry, but we're now using ammonium ions as leaving groups. So the way this is done, the procedure he developed is if you have an amine, any amine, primary, secondary, tertiary, and you do an exhaustive methylation. So you turn it into the quaternary ammonium salt, meaning all alkyl groups now on the nitrogen, and you use a cheap alkylating agent, and that one is methyl iodide. Okay? So you just dump in methyl over alkylate until you're done. Okay? So you're actually exploiting now the first synthesis of amines that we discussed a week ago, which had the problem of overalkylation, namely the SN2 reaction of an amine with a haloalkane. You're now using the fact that it's overalkylating. So you're adding excess methyl iodide, and you methylate once, deprotonate, methylate again, until you're at the ammonium stage. Okay, so for this guy, you methylate once, deprotonate again, deprotonate, and then a third time. So you get the corresponding ammonium salt that is shown here or shown here. Okay? And in the second step, you treat that with base. Now, you could use the bases that you've normally used. The preferred base actually is a kind of odd one, is silver oxide in water, which in essence is silver hydroxide. So it's not sodium hydroxide. They don't use LDA or P-butoxide. It's silver hydroxide. And the reason is that silver forms complexes with amines, so it enables the reaction. It facilitates the reaction, so it's particularly smooth. If you can't remember, silver hydroxide will give you other bases, okay, because it will work only not as well, also with other bases. But that's the base of choice. And so for this case here, you can see butanamine, excess methyl iodide. You add some carbonate to mop up the HI that you're forming from this proton here and the I here to prevent it, you buffer it, basically prevent it for the pH not to go too low. But that's irrelevant for you. All you need is methyl iodide, and you use excess, and that gives you the quaternary ammonium ion, and then silver oxide water. And via this transition state, which is the classical E2 transition state, the anti-configuration of the proton that is being ripped off and the leaving group, which means, by the way, of course, that if you have stereocenters here, other alkyl groups, and R and S is defined, they will line up perfectly to give you a stereochemically defined double bond. So keep that in mind. And E2 occurs, and there's your double bond. Okay? And the other product goes as water and the trimethyl amine. So this is particularly useful and has been used as such over the decades for degradation of amines, particularly alkaloid natural products. Alkaloids, you may recall, it's a common term for natural products that contain nitrogen, so naturally occurring amines. And one of them is this one, actually, N-methyl azocycloheptane. We'll learn how to name these guys in chapter 25. 7-membered ring with a nitrogen here and a methyl here. And this example shows you how one can degrade this by breaking the bonds to nitrogen both to the right and to the left. And what you do is in a two-step process, first you methylate again to make the ammonium salt. Silver oxide gives you elimination, and it puts in one double bond, and you've cleaved one carbon-nitrogen bond. Okay? And I've purposely put in the proton that's being plugged off with the base. Okay, that gives you the double bond here, and this, of course, is the ammonium leaving group. So it's the N-dimethylamine system that gets you here. Now, since this is a cyclic system, the leaving group has left this carbon here, but it's still attached to the molecule. It's the classic situation of a cyclic unraveling. But you can see that this is actually a ring-opening reaction because you're breaking the carbon-nitrogen bond. And you don't have to stop here. You can keep going. Methylate again. Gives you the trimethylammonium. Again, base. Now you're going after this proton, put in the double bond here, and it gives you this product here, which I've left in its arrangement so you can see where it's coming from. And so in this way, using what's called exhaustive methylation and the Hofmann degradation, Hofmann elimination, you can rip out the nitrogen and turn all the carbons in the neighborhood of the nitrogen into double bonds. And you can see, since nitrogen is trivalent, in principle, in a more elaborate system, you could do this 3 times and put in 3 double bonds into a molecule. Okay? So this is a pretty powerful tool to unravel chemically complex structures and turn them into simpler ones. So the second reaction is a piece of vocabulary that you should remember. And on first sight, it looks like a crazy reaction, for starters, and hard to fathom and hard to memorize. The way to understand this is to recognize that, in fact, this process is nothing else but the nitrogen analog of an aldol addition reaction. Okay? And we'll go through this slowly. So this was discovered by this guy here, Manik, the turn of the century. He lived until shortly after the war. It's called the Manik reaction. And it, in essence, amounts to an amino methylation of a ketone, where you can introduce, you're making a new bond, where you introduce a nitrogen and a new carbon next to an existing carbonyl function. And the setup is quite remarkable, actually. And it's remarkable this reaction works. If you had sat down, if I had given you this mixture, okay, this plus that, and I'd asked you to write down all the possible products that you can imagine from this, you would have come up with 10, 15 different products, maybe more. Okay? And the reason that this works is, again, a classic case. It's sort of like the aldol condensation, only worse or better, depending on your point of view, that everything is reversible. So this melange, this mixture, has a chance to go into all kinds of tangents. It goes back and forth, back and forth. Eventually, it finds the product. And part of the trick is that the product is an amine, that it shows up as an ammonium salt because the reaction has to be carried out under acidic conditions. So it pulls out the amine from the reaction mixture as an ammonium salt, and that is part of the reason why this goes. And, of course, thermodynamically is also the preferred structure. So, again, in an equilibrium situation, Le Chatelier's principle, everything eventually filters off to the most stable compound. So what you do as a starting setup is you use two carbonyl compounds, one of which is more reactive than the other. So typically it involves a ketone and an aldehyde. We know that aldehydes are more reactive than ketones. Or two aldehydes, one of which is typically formaldehyde, because formaldehyde is, in the simple aldehydes, the most reactive. Okay? Or you can take something like trichloroacetaldehyde versus normal acetaldehyde, stuff like that. So it has to be two carbonyl compounds that show a pronounced difference in reactivity. So up here, it's a ketone and formaldehyde. Okay? And you dump in an amine. Okay? It can be a primary amine, secondary amine, but one hydrogen has to be left here. So primary and secondary amine. And you do this under acidic conditions, HCl, and out comes the product. And if you look at this carefully, you realize that one could potentially expect that the more reactive carbonyl function in the presence of the nucleophile, the only nucleophile in the mixture, namely the amine, will form an imine. And since this is under acidic conditions, that imine will be an aminimine, okay, reprotonated. In other words, remember we discussed that when we formed imines, you're forming the nitrogen analog of the aldehyde. Imines are nitrogen analogs of aldehydes. And so when you set up this equilibrium, this CH2O turns into CH2N as an iminium. And as the iminium species, it can react with the enol of the less reactive carbonyl by a process that is, in terms of arrow pushing, identical to the aldol addition. The only difference is charges. You have a neutral nucleophile as opposed to an enolate. You have the enol. And you have a charged electrophile, an aminimine, as opposed to a neutral other carbonyl compound in the normal aldol addition reaction. So the charge differential between the two is still the same, but now you're one notch up. You added a plus charge to both sides, as it were. And this gives a new bond, okay? So it's like the enol having added to the imine to the CN double bond. And it winds up as the ammonium salt initially in the mixture, and then if you subject that to basic workup, you get the free amine. So this is illustrated here again. This is now for a normal aldehyde, again with formaldehyde as the counterpart, and now we're using methylamine. And that will form the imine, and now the enol derived from the aldehyde will add to the aminimine under acidic conditions, and here I'm actually adding, explicitly stating the basic workup, and so I'm writing the free amine that shows up. So these are very high-yielding reactions, even though dozens and dozens of other compounds are floating around there and are formed in an equilibrium situation. So this was a lot of verbiage. Let's actually look at the details of this mechanism, and so we're going to do that on the board. And point out the similarity to the aldol. So we're starting with a ketone, and so I'm using the same guys as up there, and hang on, we'll do that in the second step. Mechanistically, we should start with the imine formation. So the fastest thing that will happen is the formaldehyde reacting with the amine, and this goes by the classical, and I won't write that out, addition reaction. Okay, so nucleophilic attack, the electron pair goes out here, and that proton then winds up on the OH. That gives you the hemiaminal. And the hemiaminal, by the classic dehydration mechanism, will give you the aminimine, which is this. Now, if you were to do this with methylamine or methylamine, that is two hydrogens on here, you would still have a proton here, and in the imine formation, you would deprotonate and isolate the imine. But this is under acidic conditions, so and you're not working up in a mixture with water or anything, so most of it will be protonated. So you get the aminimine regardless, okay? In this case, it's automatically aminimine because you have two alkyl groups, two methyl groups on this guy. So this will be the equivalent, I call it CF, compared to a carbonyl in the aldol. Okay? Notice that this is positively charged. Separately, parallel to this, the cyclohexanone will set up an equilibrium with the corresponding enol. Again, I won't write the mechanism for that, but this is under acidic conditions, so this goes, as you know, by protonation of the oxygen first and then deprotonation here. Okay? Basically a hydrogen shuttle. Okay? And that gives you the enol. The enol part is the equivalent of the enolate